Good afternoon, everybody. My name is Julian Rozo. I'm alongside my colleagues Wladimir, Valdenegro, and Jose Martinez. And today we're going to be presenting our senior design project. Our senior design project constitutes being a part of a competition. There's a world-renowned competition sponsored by Lockheed Martin, and this competition is the SAE Aero design competition. Our objective for this presentation is to introduce to you our project, and basically our objective for our project is to design a lightweight micro-class UAV vehicle that can be easily deployed and be able to fit in a 6-inch diameter tubing. Our goal is to obtain a payload fraction of 4:1, meaning that our aircraft needs to be able to lift 4 times its empty weight. Our biggest motivation, I'll say, is being a part of FIU. We don't per se have an aerospace field here at FIU, but we do have a lot of clubs that are involved. So we want to design this project and pursuing the knowledge of aerospace and expanding this in the Florida International University.
Alright, one of the biggest things when it comes to aircraft design is you have to understand the history of aircraft design. The first aircraft was probably developed by Leonardo da Vinci. It wasn't really a traditional aircraft per se. It was ornithopter. It worked like flapping wings. So that went on, and then it wasn't until the 1900s that we had the self-sustained aircraft by the Wright brothers, called the Wright Flagler. And then in a little bit underneath, in 60 to 70 years, we have man landing on the moon. So these concepts and designs build upon each other. So next slide. One of the biggest things we're going to be looking at, besides our traditional textbooks we have here at school, is aircraft design conceptual approach by Dihedral. It's very well known in the industry. So we have a lot of equations come from that. And one of the beautiful things about aircraft design that a lot of the parameters are dimensionless, so they can be scaled up or scaled down. So you can design with this way. You can design a micro UAV, or you can design a full-blown 1.7. Next slide. So the global learning awareness. I think one of the biggest, most important part about this competition is the fact that it's world-renowned. So we have students from Brazil, from all parts of America, from South America. They come together, and even though engineering concepts are relatively universal, the way you approach these concepts are not. So someone who's from Brazil will completely approach this problem in a different way. And we hope by participating in this project, we'll be able to learn a little bit from everybody and give a little bit to everybody. All right, so some related standards. Although this competition does have some standards set by the organization SAE, two of the biggest standards we have to take a look at is the FCC radio safety requirement. We have to make sure the frequency we broadcast at controlling our remote control UAV does not interfere with emergency signals or any other broadcasts that are busy. Another really big standard we have to abide by is the FAA, the Federal Aviation Administration requirement that if our UAV weighs over 5 pounds, we have to get it registered by them. This is a non-issue though. It's as simple as paying $5. Next slide. All right, so these are some design formulations we use to make our initial designs. I want to bring into attention 2 concepts up here. They're really more like performance modifiers. We call them the coefficient of lift and the coefficient of drag. You'll see why they're important on the next slide. All right, so when it comes to aircraft design, we look at different types of airfoils and how they come about together. Airfoils have different properties and performance characteristics at different angle of attack. An angle of attack is the angle relative to the free flow airstream. So we can see as the angle of attack increases, the coefficient of drag increases as well. So we want to keep a fine line between performance and feasibility.
As my friend Vladimir was explaining, the coefficient of lift is also very important. As you increase the angle of attack of the airplane, the coefficient of lift increases as well. There's a boundary where this coefficient of lift is going to break in a way that as the angle of attack increases, you're going to lose some lift. And that creates instability for the aircraft, and you can definitely crash the aircraft. The center of moment for our design is very important. As we're going with a flying wing design, we don't have a vertical stabilizer. Therefore, as you can see here on the y-axis of this graph, The center of moment is relative to the center of gravity of the aircraft too as well, as we want to achieve the center of moment to be as close to zero as possible. Therefore, we're choosing airfoils that are going to give us those characteristics.
So we're going to talk a little bit about the design alternatives. This is a competition, therefore we want to achieve the most competitive design that takes into consideration and into account and brings in basically every improvement that has been made to aircraft ever since they first start being developed. One of them being the dihedral angle. So when you have a dihedral angle on the aircraft, it makes it inherently stable. This is done by differential lift. So when you're banking, the banked wing will produce less lift than the one that's more horizontal to the streamline. Therefore, it will have a tendency to balance itself out. So we intend to use this. Another thing that we have to take into account is that because of the competition constraint of putting the aircraft in a 6-inch diameter tube, we have a limited port, which will inherently make our aircraft to have a very high aspect ratio compared to other aircraft with similar performance and similar characteristics. And lastly, we have to worry about the airfoil that we have chosen, because this not having a horizontal stabilizer, we need to counteract the moment, the pitching moment that the aircraft, the conventional airfoil would produce, so therefore we're using reflex airfoils. So this slide over here is an illustration of what happens when you use another performance improving method, which is basically taper ratio. On the first picture right there on the flank, you can see a very large, induced drag plot. It's not really numerical, it's more a graphical representation of what will happen as you increase the taper ratio. So the closer it is to 0.5, the less you experience induced drag, and on the last snapshot you can see what they're called rate wingtips. These are used on very cutting-edge plane designs nowadays, and as you can see, it basically cuts down the induced drag to it's like. Another characteristic that we're going to be using is sweep. Normally speaking, when you want to use sweep when you have very high speed flight. However, for our application, we want to use sweep angles because they will make the plane or the flying wing more stable. This is done because it pushes back the center of pressure aft, and therefore we can put the fuselage and the payload a little bit more back, and we can play around with the fuselage size.
So giving the alternative design, this is our first alternative design. You have a plank wing right here in front of you. The plank wing is pretty much the definition of no sweep angle. So ideally, this is not something that we desire, as it doesn't bring stability to our aircraft. There's some pros to this design though. It's easily able to store in the container, as we don't have any twists or dihedral angles. Also, it's the lowest. It has the lowest amount of drag and induced into the aircraft, as since you don't have a sweep angle, we're not gonna have a high drag.
Our second design alternative is introducing the sweep angle. Not a drastic one per se, but enough to provide stability along the longitude axis. The bad part about this is that we do reduce some surface area, and the way that an airplane wing works, the more surface area you have, the more lift you generate, right? So now we have less surface area, even though our wing is more effective and efficient, our wing loading increases. And with an increased wing loading, there's more force per unit on the wing than before compared to the plane.
Lastly, we have our proposed design. It combines 3 different types of airfoil. It has a conventional airfoil closer to the fuselage of the aircraft. As I said earlier, this type of airfoil produces a pitching moment. So in order to counter that, we actually use a reflex airfoil from this section over here all the way to the back. Another performance enhancing characteristic is the inclusion of taper ratios and winglets. So winglets work kind of like the rate wingtips that I was talking about earlier. They basically prevent induced drag, and this is done by preventing the circulatory flow at the tip of the wings, which basically hurts your efficiency of the aircraft. One of the drawbacks of this design is that it's going to be very difficult to manufacture. Like I said, it has 3 different types of airfoils that we have to integrate, somehow model, and somehow manufacture. One of the pros, however, is that it's going to be extremely efficient. If we use the right choice of materials and the right manufacturing method, we can actually achieve something that is very light. Just you lack the horizontal and vertical stabilizers, it will be very quick to assemble. It's just a win. This is a quick rundown of our projected costs. Some of these things are approximations. We really have no way of saying how much we're going to use or how many prototypes we're going to build. we're going to assume that if we were to build one plane made out of balsa woods in a typical ribbon spar fashion with some ultra coat, it would cost about $400 processing and basically everything that we have to outsource. We have to buy something or get something laser craft. If we were to go with composites, it would bring the cost up to almost $800, $900, depending on the fiber that we use. If we use fiberglass or carbon fiber, the processing, if we want to use a mold, basically we want to use foams, or there's too many factors, realistically speaking. So we just projected the cost for one plane. Naturally, if you were to bring this out to a more manufacturing world and make this into a mass production type of endeavor, then the cost will go down, especially with the materials and the process. So this is our projected timeline. It's actually not projected. We came up with this 3 months ago. We're right on schedule. We predict, and this is quite true, that our literature survey will take a very long time. We can't claim that we know everything by now. That is not true. You could potentially ask us a question right now and we might not know, because we will always encounter a problem that we have to go back, get more information, and try to make an informed decision on our engineering analysis. And hopefully we can start manufacturing come next semester. We will do ANSI simulations during the winter break, and that basically covers the course of the year.
Thank you so much, and I open the floor for discussion, questions, or concerns. Yes.
Now, something I've always experienced is the lack of stability with flying wings. From the shape that you're showing here, what you're looking for to increase your stability is a 90-degree angle of both of your wing sections. You're showing a very shallow angle, which worries me that your plane is just going to go into a spin and you just won't recover, or any abnormal loading will cause it to go into a flat spin and come down to crash.
So the thing with flying wings is they're not aerobatic aircraft. They're meant to have very specific paths. If you look at the planes that have been developed that are flying wings, such as the V2, they don't do maneuvers that are extreme. They follow a particular stability pattern where if they increase the angle of attack more than they're supposed to, they will basically pitch up and lose control. It actually kind of happened on one of them. The one that has crashed, that's what happened to it. The other consideration, and what you're talking about, the sweep angle, you can actually play with the sweep angle depending on a combination of twist on the airfoil and the airfoil that you use. Like I said, the reflex airfoils have the tendency by design to counter that pitching moment. So you can have a flying plane that will be stable without no sweep. So you can actually use a conventional airfoil and add sweep and twist to the wings, and you can have like a sweep angle, and you can actually make any airfoil a flying wing with the proper amount of twist and sweep back.
And to add what he said, we are using currently for a quick design phase this program called XLR5. It does very quick CFD analysis, and we just put in our parameters, and it's parametric. So it will tell us whether, it will give us a good idea of whether the wing is stable or not at different flight conditions, at different wrinkle numbers, at different altitudes. It's all programmable. This is just to make sure we're heading on the right track. Obviously, once we have the sizing set down, the sizing in a wing is very, very important. Once we have the sizing set down, we will introduce more sophisticated programs such as ANSYS and really, truly calculate it. We're also thinking, if you can bring back the slide of the final render. Well, this is a fuselage, right? So on a flying wing, you have the center of pressure where your lifting force is acting on, and your center of mass after the payload is at. This fuselage is not going to be a 1-to-1 ratio of the payload. It's going to have some shimmy space. So we would be able to move the payload forward or backwards depending on the characteristics of flight. Also, too, we have to make sure as part of the competition rules that the wing has to be flown without payload and with payload. So we do need some sort of roofing where we can adjust the weight, and therefore we'll have stability at 6 pounds and we'll have stability at 1 pound.
So there's 3 ways you make a flying wing stable. You add dihedral, you sweep the wings, and you increase your drag at the wingtips. You have very low dihedral, you don't have a lot of sweep, and you're removing your drag using winglets. So I am concerned that even though your CFD is telling you have a stable wing, your loading, your pressure loading is going to give you a different story.
Mr. Felix mentioned that he did include 3 different types of airfoils, so you could potentially also increase the stability of flying wing by adding different sections with different types of airfoil characteristics. So for example, I'm not sure if you want to elaborate on this, but for example, you might want more of a reflex airfoil in the middle. I'm not sure.
Right, so in our case, this is our final design. We didn't just come up with this. We iterated a lot. It was initially a pure reflex airfoil to make sure that we had exactly what we were talking about, that the drag was appropriate, because what you're talking about is basically having a counter lift in the opposite direction of what you normally want to counter that pitching moment. However, we found that by increasing the sweep, we could actually get away by using a conventional airfoil with very high lift characteristics. And the one that we picked is the Sealing 1223, which is renowned, at least in the world of RC aircraft, to have very good lift characteristics at very low Reynolds numbers. And we combine it by the best performing reflex airfoil that they have available right now, which is basically from this end to the end, to the wingtip, and that basically makes it stable. Alongside with playing with the center of mass, like I said, there's a lot of things that go into this. The flying wheel will be unstable at most of the ranges. It has a very small stability margin. It can only fly at certain degrees. It cannot do aerobatics. It's a very mission-specific aircraft that has to do exactly what
and to elaborate what he says, the competition does have certain rule. We're limited to a 60-second flight time. We also have a certain track, a circuit, which is we go straight to 2 banks, come back around, do 2 banks. So we are not planning on doing any sort of rolls, any sort of acrobatic performance. Various mission specific.
I'm not talking about any of that, right? Are you flying in calm conditions? Do you know what your wind is going to be? It is going to be calm?
It's here in Orlando. This year is here in Orlando, so it should be pretty calm, relatively calm.
Right. You're flying a balsa airplane, which
we don't know if it's composite or balsa, depending on our sponsors, if they come through.
all right, so you're flying a highly light aircraft.
Right.
That is, I'm just I'm not criticizing your design, I'm just telling you, keep these things into consideration, because you mentioned the B-2 bomber. The B-2 bomber has millions and millions of computations per second that alters the wing geometry to keep it stable. Yours doesn't, right? Yours is not going to have that. Which, by the way, you didn't go into any of the servo controls that you would implement into your wing. Now you have different weights, batteries. Your rods are probably going to be either on the inside or on the outside. So those are elements that are not part of your computation. So you just keep that in mind when you're doing your analysis, because all these little factors in the big picture, in a wing, in an airplane that is 27 feet long, is not the same thing as when you're 12 inches long.
Completely different airspeed, correct.
A 1 knot wind up there is going to frisbee your airplane. So you need to consider these things. Part of your analysis, you have a high wingspan under pressure load. You need to run flutter testing. Your wings are going to start fluttering at a certain condition, and you might just clap. So you need to consider that as well. And my last point is, you mentioned balsa, but at the same time, your design is supposed to be packed into a tube. Balsa is very fragile. How are you going to manage to pack and unpack this thing or unroll this thing without potentially damaging the balsa structure?
Well, that's where the engineering comes in. Whether or not we're adding a stress skin to this, made out of ultracold or carbon fiber, or we're just using a carbon, a balsa spar going down the wing. Balsa would just be one of the components that is in the aircraft. We'll be using most likely carbon fiber ribs with some sort of a balsa insert inside. But the whole point is to control these 2 uses of carbon fiber and balsa to make that as light as possible. This is not to say we're going to construct the wing only with balsa. It is one of the materials we are using. If we want to construct with only balsa, the option is there. But since balsa is weak, we are not planning on doing that.
is this something you're supposed to fit in a tube and then
Yes, sir.
assemble, or
So-
as soon
yes.
as you pop it out, it
Well, it can be
opens up?
It can be either or, depending on your weight analysis, depending if you planned it well. Right now, we're planning on having a modular fuselage. So the fuselage center will be the size of maybe a graphic calculator, and we'll have some sort of struts or inserts. We'll be able to slide the wing outside of the tube. So a 6-inch diameter PVC pipe, you slide out the wing and snap them on, almost like Legos. So that's our initial structural. That's where we want to go to. There's been teams in the past that have done a flying wing made out of an inflatable wing. There's teams that built their wings right at site. It really depends on what you want to take with the project. We believe having that modularity in our design, though, will be very popular and very, very sought after.
Last thing, I promise.
No.
When you go into that modular design, now you got to consider your loads on those specific
Right.
pins that you're attaching,
Right.
because you're no longer distributing that load over your airfoil section. It's now being transferred through whatever joint you're putting on that.
And during a bank, we might experience 3Gs or 4Gs times the 4. So quick off the bat, 6 times 3 will be probably 18 pounds on those joints. Divided by 2 wings, maybe 9 on a good day. Add some factor of safety. Yeah, we're looking about 15 or 14 pounds off the top of my head. But we believe that's doable with carbon fiber, some sort of carbon fiber styrofoam integration. Maybe have a hollow carbon fiber tube and run styrofoam inside. Styrofoam for compression, carbon fiber for tension. The materials are there. We're not using next gen space gen materials. The materials are there. All that's left is to do the analysis and do it right. But we believe this is very feasible and within our grasp.
So if you're doing modularity, how are you gonna? First of all, do you have control surfaces?
Yes, sir.
Yes.
So if you're having modular wings, how do you connect your control surfaces to the
Great question.
electrical?
Okay, so we can do either one of two things. We can actually have some sort of banana plugs or some sort of plugs that we have to connect halfway to the back. We connect the wings, we connect the plugs. There we go. Or if budget permits, what we're thinking of is having contacts. So on the wing itself, where it connects to the fuselage, we run the wires internally, and we have two contact points for the servos on each wing. So all we have to do is snap and play, and we don't worry about having to plug in cables. But either or, whether it's cables or whether it's contacts, these servos are going to be connected to the main power source, which is located on the fuselage.
So I want to build into that and say that we definitely want to do away with the wires because they act unnecessary weight in our case, especially connectors. We're really looking into some sort of integrated banana or maybe a DIN type connector that has that compression when you connect them together, that they won't come loose during vibrations or during forces or something like that.
So if you use base-mounted pins or contacts, as you're saying, you need a constant load, and using pins, you're not going to have any retention on your wing. So I'm confused as to how you're going to, first of all, how your wing's going to stay in place if you're using pins, unless you're press fitting them in.
Right. Or we can use neodymium magnets. Something with a pulling force of 50 pounds or 40 pounds, all depending on our weight consumption, our weight budget. If we use neodymium magnets, yeah, we introduce an RF interference, but I'm sure we can do away with that with some shielding. But it all depends on the structural design. Thus, like I said, the materials are there, the structure is there. The engineering comes putting something very, very lightweight that has an empty weight of the craft and carrying as much power. But yeah, I believe that's like a non-issue. We can easily resolve that. We have that. We've done stuff before.
And I want to build into that. I mean, we haven't talked about manufacturing at all. This is more into the manufacturing, how we're going to make it and put it together. We kind of do it on the spot right now.
Things that we've discussed.
That's great, but the problem is that avionics always gets left out, and unfortunately, without avionics, your plane doesn't do anything. Which is the problem that I face all the time at work. Is everybody's like, oh, the structure's fine, it'll work. Avionics is a service, when in actuality, without control systems, nothing works in this day and age.
So we're only really looking at a battery, a motor, a propeller, an ESC, a transmitter. So the avionics are not space age or space jet. They're very
servos.
To be fair,
rods.
Right. So these are they're very I wouldn't say primitive, but they're very documented. It's very documented, very, very well documented. People have done it before, people will do it in the future. military handheld military aircraft that they launch UAVs. They're also they work on the same propellers, on the same motors. It's really avionics is not a big deal. We are, by the competition's rule, we are allowed to put a gyroscope on there. We are considering of coding maybe some sort of auto stabilizer to it, but that's for future work. That's for something if time permits, if budget permits. But as in the servos, as in the motor, the propeller, the control rods, the ESC, the transmitter, it's as easy as doing your research and finding what's best suited for your aircraft. Yes, sir.
Please, go ahead.
Why a flying wing?
Perfect question.
So I will take that one because I was probably the most opposed to the idea because you can have very efficient, let's call it conventional airplane designs that can lift a lot of weight. However, a flying wing gives us two main benefits that nothing else gives us is our modulability. So basically we can put it together really quick. It's innovative in a way that there's only so few aircraft currently flying the flying wing configuration. We're pushing everything outside of the boundary. When you look at a regular cargo plane, it will have a payload fraction of maybe 2, maybe 3 at most. This thing will have a payload fraction of 4. We're pushing towards 5. So this is pushing every single envelope. When we look at a graph or straight studies of maybe wing loading or maybe thrust that we need or maybe the stresses or the aerodynamic loads that we're experiencing, everything is off the charts. So we want to do it because it's innovative. We really feel it hasn't been done before, and we want to like test ourselves as mechanical engineers, like really push it, see how far we can get with it.
Like why not a flying wing? It's a little bit more computational analysis and a little bit more math, but we found that it's, I mean, as slack as it sounds, we found that there's a very cool factor behind the flying wing. There's something very iconic of the scene of flying wing. And to add to what he says, we also reduce a lot of weight. Technical wise, we reduce a lot of weight because we no longer need a vertical stabilizer. We no longer need a horizontal stabilizer. We reduce the actual package size, so we're only focusing on the entire wingspan instead of the actual longitude on the longitude axis. So we have a lot of weight reduction and a lot of size reduction. Yeah, it comes at a cost of CO being affected, or coefficient of lift being affected, but that can be counteracted by a bigger motor or a bigger propeller to generate more power. But yeah, it was that. We thought it was a good challenge. It was because conventional aircraft design, it's fun and all, but we did not see the challenge in that. We saw a challenge in that.
Your propellers in front?
Right now we're having a polar propeller configuration. According to sources, it was the most efficient one. We are thinking of going pusher only if our center of moment is unstable. We'll have that luxury to change. With our modularity design, we have that luxury of changing and shifting things around depending on the flight characteristics we want. So that's something up to the future, polar pusher.
So considering how unstable this design tends to be, aren't you concerned that you have actually no instrumentation to tell you whether or not you're flying too aggressively? It sounds like you're going to need a lot of training on this to successfully fly, which seems like not the best amount of use of your time. Like,
well, look,
so we
have 2 pilots who are willing to fly this for us. They are very, very well versed. Very rare. They have been flying RC aircraft for how many years? They're also members of the FAE Aerospace Club, so they are allowed by competition rules to fly the aircraft for us. We are doing the engineering, they'll be our pilot. As far as the instability, we're out of the competition once the aircraft turns around. So there's no barrel rolls, no aileron rolls. So once the aircraft's upside down, we're disqualified. So we're going to try our best to make this as stable as possible. But as far as the pilot and as far as that skill comes, we do have that covered.
We are allowed to have some sort of control.
We have the gyroscopic assist too that we could implement depending on time constraints and budgetary constraints.
We're done.
Yeah.
It's time.
If you have any further questions, feel free to direct it to our professor. Feel free to talk to us. We're looking for sponsors.